Hello there, how are you? Welcome to Maths for U By Attaur Rahman. Please do subscribe my channel, like it, and don't forget to share with your near ones. Hello guys, I am Attaur Rahman from Maths for U By Attaur Rahman. In this session we are going to discuss the procedure of solving the system of linear equations through the inversion method along with examples. So let's start by taking the system of linear equations containing two unknowns. Consider the system of two non-homogeneous linear equations in two variables x and y. That is, a into x plus b into y is equal to and c into x plus d into y is equal to n. So, let's consider equations, and now let us name these equations as equation 1 and equation 2. This system in matrix notation can be written as: we constitute a matrix called the coefficient matrix like this. The coefficients of the unknown variables, x and y, that is, a and b in the first equation, are written in the first row, while the coefficients of the unknown variables, x and y in the second equation, that is, c and d, are written in the second row. Along with this coefficient matrix, we have in multiplication a column matrix which comprises of the unknown variables, x and y, involved in the given system of equations. On the right of the above equations, we have constants, m and n, which we will write in a column matrix on the right side of the matrix form of the system. Since we know that matrices are generally denoted by the uppercase letters, so it is customary to denote the coefficient matrix by A, the matrix of the unknown variables by x, and matrix of constants on the right-hand side by b. Thus we have A into x is equal to b. Now if A is a non-singular matrix, as if A determinant is not equal to 0, then the system will have a solution. Since we know that matrix multiplication is not commutative in general, that is, AB is not equal to B A. So, we pre-multiplying both sides of equation star by A inverse, that is. Here we will use associative law of multiplication. Thus we have A inverse into A along with x is equal to A inverse into B. Since A inverse and A are multiplicative inverses of each other, so their product will give identity matrix of order 2. That is, now the product of identity matrix and the matrix X gives back the matrix X. Thus we obtain an equation for the solution of inversion method. That is, X is equal to A inverse into B. Thus in this equation, we first need to find the inverse of the matrix A. That is, A inverse is equal to 1 upon the determinant of A time adjoint of the matrix A. So, first of all we will find the inverse of the matrix A, for which we must go to work out the determinant of the matrix A, to check out whether the matrix A is singular or non-singular. If the determinant of the matrix A is 0, that is, the matrix is singular, then the given system of non-homogeneous line equations will have no solution. And if the determinant of matrix A is not equal to 0, that is, the matrix A is non-singular, then the given system of non-homogeneous linear equations will have a solution. Since we know that the determinant of the 2 by 2 matrix can be worked out as: we first multiply the elements of the main diagonal, that is A multiplied by D, and then subtract the product of the elements of the skew diagonal, that is B multiplied by C. We suppose that AD minus BC is not equal to 0, thus the given system has a solution. Next, to find the adjoint of the matrix A. As we know that the A adjoint of the 2 by 2 matrix is easily obtained by just interchanging the places of the elements of the main diagonal and changing signs of the elements of the skew diagonal. Now putting the values of the determinant of A and the adjoint of the matrix A in equation 4 to get the inverse of the matrix A. That is, now finally, we will use equation 3 to get the solution of the given system of linear equations. That is, x is equal to 1 upon the value of the determinant of the matrix A, along with the adjoint of the matrix A, multiplied by the matrix of the constants on the right-hand side of equation 3. That is, by the matrix B. Since the order of this matrix is 2 by 2, and that of this matrix is 2 by 1. As the number of columns of this matrix is 2 and the number of rows of this one is also 2, that is, they are equal, so these matrices are conformable for multiplication. Since we know that matrices multiplication can best be remembered as row-column multiplication. So according to the definition of the product of two matrices, the elements of the resultant matrix is the sum of the product of the corresponding elements of the row of the first matrix with the corresponding elements of the column of the second matrix. Now, by the definition of scalar multiplication, we multiply this factor to each member of this matrix. That is, the matrix X of the unknown variables X and Y is obtained by dividing each element of the matrix by the value of the determinant of the matrix A. That is, the element at the first row and first column of this newly obtained matrix. That is, D n minus B n is divided by the value of the determinant of the matrix A, that is, by A D minus BC. Similarly, the element at second row and first column, that is, negative C dam plus A n, is divided by the value of the determinant of A, that is, by A D minus B C. Now, by the definition of equality of two matrices, we have the value X and Y. X is equal to D dam minus B n divided by A D minus B C, and Y is equal to negative C dam plus A n divided by A D minus B C, which is the required values of the unknown variables X and Y. Let us consider an example. Dears, in this example, we will try to solve the system of linear equations by using the inversion method, and we confine ourselves to just two equations, that is, x minus 3 times y equals 0, and 2 times x plus y equals 7. Since we have given two linear equations in two variables, x and y, that is, the number of equations is equal to the number of variables, so the system of equations is consistent. That is, the system of equations has a solution. Let us name these equations as equation 1 and equation 2. These equations can be written in the matrix form as: we will write the coefficients of the variables in equation 1 in the first row, while the coefficients of the variables in equation 2 in the second row, as the coefficient of the x in the first equation is 1, and the coefficient of the y is negative 3. Similarly, the coefficient of the x in second equation is 2, and that of y is 1. As this matrix contained only coefficients, that's why it is called coefficient matrix. Along with this coefficient matrix, we have a column matrix comprising of the unknown variables x and y, called the matrix of unknown variables. On the right of the above equations, we have constants 0 and 7, which we will write in a column matrix as. Since matrices are denoted by the uppercase letters, and it is customary to denote this coefficient matrix by eta, the matrix of the unknown variables by x, and the matrix of the constants is denoted by b. Thus, equation star takes the form, and its solution is given by. And let mark this as equation 3. In this equation 3, first we will find the inverse of the matrix A by using the well-known formula for the inverse of the matrix. That is, the inverse of the matrix A is equal to 1 upon the determinant of the matrix A multiplied by the adjoint of the matrix A. Let us find the determinant of the matrix A. That is, we will put the elements of the matrix A in the vertical bars called the determinant of the matrix A. As we know that, to evaluate the determinant of a 2 by 2 square matrix, we first multiply the elements lying on the principal diagonal and then subtract the product of the elements lying on the skewed diagonal. That is, 1 times 1 minus negative 3 times 2. Thus, we obtain 1 plus 6 equal to 7, which is a non-zero quantity. Since the determinant of the matrix A is not equal to 0, so the matrix A is non-singular, and hence, A inverse exists, and consequently the solution of the system exists. Our next aim is to find adjoint of the matrix A. As the adjoint of the square matrix of order 2 can be found by interchanging the positions of the elements lying on the main diagonal, and then changing the signs of the elements lying on the skewed diagonal. Hence the inverse of the matrix A is given by. Now finally we will use equation 3 to find the solution of the given system of equations, that is x is equal to inverse of the matrix A multiplied by the matrix B. Since x is a matrix containing the unknown variables x and y, so it is equal to this column matrix. Further, these two matrices are conformable for multiplication, so they can be multiplied by using the rule row-column multiplication. This further implies the column matrix containing x and y is equal to 1 upon 7 multiplied by the column matrix containing 21 and 7. Now by the definition of scalar multiplication, 1 upon 7 will be multiplied to each term of this matrix. That is, now by simplifying, we have finally, by using the definition of equality of two matrices, we have x is equal to 3, and y is equal to 1. Thus the solution set is given by. Hope this lecture has given you a clear idea to understand how to find the solution to the system of linear equations in two variables. Thanks for watching it. Meet you in the next video. Till that, bye bye.